All right, we'll go ahead and get started. We would like to welcome you to today's webinar, Revealing and Quantifying Hydrocarbons, Methane and VOC Emissions Using Infrared Imagery. This webinar is brought to you by Telops and is the first webinar in a series of 3. As a reminder, you will receive the recording of this webinar along with a PDF version of the slides after the conclusion of today's presentation. If you have any questions, please type your question in the Q&A area at the bottom of your screen, and your question will be addressed at the end of the presentation. We encourage you to type in your questions during the presentation as you have them. Please join me in welcoming today's presenter, Jean-Philippe Gagnon. Jean-Philippe is a field application scientist at Telops, where he has been involved in the development of their line of infrared cameras and hyperspectral infrared imagers since 2005. I'll hand it over to you, Jean-Philippe.
Thanks, Jessica. Hello, everyone. Let me first thank the Energy Conference Network for promoting and giving us the chance to present here today. So as Jessica says, my name is Jean-Philippe Gagnon. I'm a field application engineer at Telops. I've been with Telops since 2005. So my background is in physics mostly. So and at Telops, Jessica mentioned, I spent quite a bit of my time using infrared cameras that we manufacture here to look at various applications. And one of them, which I will present on today, is using infrared imagery, hyperspectral infrared imagery, to detect and quantify either greenhouse gases, organic volatile organic compounds emissions from various sources. So that's the subject of my presentation here today. So I hope you'll enjoy this presentation. And yeah, as Jessica mentioned, don't hesitate to write any questions that come up during the webinar. I'll spend a little bit of time going through all the questions at the end. So let's dig in right away with the outline of the presentation. So I'll do like a very brief introduction about the company, about Telops. And then I'll jump in and address or talk about the problems or challenges that we're facing here today with emissions regulation. Then I'll present the Hypercam. So this is the hyperspectral camera that we've been using to make those measurements. And then I'll address very briefly the principles of gas detection, identification, and quantification. So this, I think, will allow you to get a better understanding of, yes, the principles behind it and how we're able to go from, just a single image to having gas that is quantified in grams or grams per hour, for example. And then before the conclusion and key takeaways, I will present some experimental results in various applications. So one of them would be VOC emitted from industrial complex, fugitive and diffuse methane emissions from landfills, sulfur emissions from seagoing ships, and of course, all kinds of gas detections that we performed in from airborne platforms. Right, so let's address first section, so presentation about Telops. So we're located in Quebec City, for those of you who might not know. So it's eastern part of Canada. So French speaking, that's why you may have recognized the weird accent. So yes, so that's the reason why. So Telops was founded in 2000, so it's 22 years old already. And since then has grown significantly to over 90 employees now, mostly based here in Quebec, Canada, where we're headquartered. But Telops caters to an international market using offices in the US, France, and also an efficient global network of distribution and representation. Our main markets, you see images there. So we design and manufacture high-performance hyperspectral imaging systems and also infrared cameras for the defense sector, the industrial sector as well, and academic research applications, where they are used in universities and various national labs across the world. We also offer R&D services for optical systems technology development. So if you have a specific need, we can always work with you to address it and build custom systems for you. All right, that's short enough. Then let me get into the problems or challenges that we're facing here with emissions. So as you may know, so the largest source of greenhouse gas emissions from human activities in the United States, this is where I found the statistics here, is from burning fossil fuels for electricity, industry, and transportation. So electricity production generates the second largest share of greenhouse gas emissions. That is 25% of 2019 greenhouse gas emissions. So approximately 62% of our electricity comes from burning the fossil fuels, mostly coal and natural gas. So carbon dioxide makes up the vast majority of greenhouse gas emissions from the sector, but smaller amounts of methane, or CH4, and nitrous oxide are also emitted. Although greenhouse gas emissions from electricity have decreased by about 12%, recent studies show since 1990, due mainly to a shift to renewables and increase in energy efficiency throughout the chain, there's still a will to reduce emissions even further. And even though CH4 emissions or methane emissions are lower than carbon dioxide, methane has a very high propensity in absorbing and emitting infrared radiation. In fact, it is estimated to have a greenhouse warming potential of 28 to 36 times that of carbon dioxide over a 100-year period. So these economic sectors emit organic volatile compounds, or volatile organic compounds, sorry, which present potential health and safety and environmental risk, as we all know. In addition, carbon dioxide and nitrous oxides from the maritime transportation sector is responsible for a lot of SO2 emissions. Now, SO2 emissions are a precursor to acid rain and atmospheric particulates, which can lead to ocean acidification and contribute to negative human health outcome. Even though the regulation is now more strict on these kinds of emissions, it's still important to reduce them, just because the sheer number of vessels out there, its emissions are just enormous. But coming back to methane, it is emitted in large quantities also from landfills, which is not explicit in this diagram, but methane emissions are important from this sector. And methane is a landfill gas, so it originates from the decomposition of organic material as encountered in landfills. But so what is clear from the last couple of years of research and workshops, which scientists and industry leaders attend, is that there's no single technology out there that can do it all, that can measure all the emissions, all emission types in all the various applications. So basically, there's no silver bullet. So the industry is now, I think, thinking about an array of sensors or a technology toolkit benefiting from the advantages of each kind of sensor and each technology to tackle emission of different kinds and different sizes. So here I've listed kind of instrumentation it could be used to detect some potential emissions. So in the beginning, traditional sniffing techniques, which involve just bringing a point sensor detector to and going and sample the gas directly, were used. And after that came the optical gas imagers, which are infrared cameras, now commonly used to detect gaseous emissions. But this kind of technology, they lack the ability to either identify the gas species or very accurately quantify the emissions. So next come the next, I think the next generation of sensor and equipment, which one of them is based on hyperspectral, and I'll present to you how it works in a little bit. But so hyperspectral technology gives you access to the gas identification. That is, without knowing what's in front of the camera, type of gas you're looking at, it will, based on the signature that it's able to extract, it will be able to tell you what the gas is. And based on the technology also, it can quantify these emissions with very good accuracy. We can also bring that equipment in the air on a fixed wing aircraft, helicopter, or a drone, and perform these kinds of surveys from an airborne perspective. Now, these are great for detecting very large emissions, of course, whereas from the ground you can detect smaller type of emissions. And more recently, well, satellites have been used, and various satellites are now in development that are using this kind of technology from space. And these are very efficient for detecting super emitters, what we call super emitters. That is, there's very large emission sources, but are less, of course, being so far in space, they're less, the footprint on the ground that these satellites can perform is less accurate. But that's the kind of technology toolbox I think that is going to be needed if we want to reduce emissions further. All right, now let me present to you the Hypercam, our hyperspectral infrared camera that we're using here. So the you see an image here, and some images on the right-hand side that were acquired with the Hypercam throughout the years. So the first prototype we've built actually was back in 2005. So it's a proven design, and since then we've basically just added new features to it and make it even better. But yes, so the Hypercam as it stands right now, I think there's more than 70 or almost 80 units that are now operating worldwide in various research centers around the world. Yeah. So what this camera does, so it basically decomposes the light, infrared light, into different channels or different wave numbers or wavelengths. And we put those all together and create a 3D data cube with it that we can analyze further. And next slide, we'll talk about that a little bit in greater detail. So having built the ground version back in 2005, in 2008, we developed a project to bring that equipment airborne in fixed wing aircraft. Also feeling the need for gas detection in various applications, we developed since 2008 a very powerful and efficient software tools to not only visualize the gases in real time, but identify them and eventually quantify them in real time. So that's also been a very important area, development area for us. Now, as I said here, the instrument is deployed on every continent except Antarctica for now. Still working on that. And it has been used from all the way up in the Arctic to the desert environment, even to the top of volcanoes. So yeah, it's a very versatile and very efficient tool. Now, as I've said, so this kind of instrument, oh yeah, sorry. And you see here both types. So now we have the ground version of the Hypercam, which is the one at the top that you see. So it's meant to be operated on a tripod. And its airborne counterpart. So yeah, as I said here, provides real-time chemical imaging up to 5 kilometers away. We say up to 5 kilometers away because we've tested it up to that point. But basically, there's no, it's a camera. So as long as it can see through the atmosphere, it will work basically. So as opposed to other types of technology, this Hypercam is not a scanning type of equipment. So it's just a kind of a regular camera. It just stares at a scene and just collects infrared information. So yeah, it's not as if we need to scan it to obtain the data. It just sits there and we get the spectral information by looking at, spending some time looking at the scene. So it allows, the great advantages of this is that it allows detection of greenhouse gases, volatile organic compounds safely from a distance, and it's totally passive instrument. That means that there's no emissions from the camera. It just sits there and collects the light. So there's no need to send a laser beam back and forth. It's totally passive instrument. All right, so how does it work? A little bit on the inside. And as Jessica said, this is the first of a series of 3 webinars. So I'm not going to spend a whole lot of time describing the inner workings of the camera. Maybe if there's a need to, I'll address that in the later and second or third presentation. But here I just want to give you like an overview, so that you understand a little bit better how the data is produced. So basically, one measurement consists of a series of acquisitions of single images that are recorded, if you want, at different wavelengths. And we build this way kind of a data cube, as I call it. So a bunch of images recorded at different wavelengths, put that in together and create a single package of data. And that's what we call a data cube, or one measurement. So a measurement has to collect one single data cube, we need to stare at the scene for a given amount of time, which varies depending on the configuration of the camera, from just below 1 second to almost a minute or 2 minutes in the more advanced configuration. So yeah, to give you an idea how I made a little animation here. So you see that the different images are collected over time at different wavelengths. And if you select one pixel out of the image, you get the spectrum, which you can think of it as the z-axis here in this image. So every pixel has a spectrum associated to it. And when you look at the data cube, when you look at the different images, you look at the signal acquired at that wavelengths, basically. So the camera, depending on the spectral resolution that you choose, which is user selectable, you can end up with a data cube or a package of a data package composed of 10 10 images or thousands of images. So the spectrum can be very precise or very not so precise, having only 10 spectral channels. So you're really able to tailor the camera to your needs. So what this translates to in real life is that for different compounds, because each compound has its own signature, you can really look at the signature or lab measurement signature and determine which kind of precision you need, which kind of spectral resolution you need. So for gases that have a broad signal, you can allow yourself to record broad signal. Or if the gas is very narrow, has narrow spectral absorption features, then you can tailor the camera to measure optimal data. All right, so that's pretty much all I have to say on the Hypercam. If you've got any questions, type them up in the Zoom app, and I'll address them at the end. All right, so let's move on to the principles of gas detection, identification, and quantification. So again, just a high-level overview. I don't want to go through any details here. But yeah, just to give you an idea how we do it. So basically, the whole process can be decomposed into 3 different steps. First step is we want to detect and identify the compound. And this is the work that we've been doing since 2008, developing the software that can do that in real time. And you can see here an example, a screenshot of the software working live. So basically, the camera acquires the data. That's the black curve in the picture, and it compares it to a library of signature. So let's say you're interested, like here in ethene. So you select the ethene signature from the database, and the software will automatically search for any incoming data for that signature. And it does so with this GLRT algorithm. Um, but as soon as it detects pixels that corresponds to this signature, it labels them with the appropriate color in the image. So that's why you see this little pink plume in the image. Those are all the pixels that were tagged with this ethene signature. So we're using a spectral library were measured in the past in laboratory environment. So this signature library is composed of hundreds of different signatures. But if your signature is in there, we can always add it to the mix. You see only one compound here. One question you might have is, can the camera detect multiple signatures at the same time? Well, the answer is yes. And you can see here an example of a mix of two different compounds, sulfur hexafluoride or SF6 and ammonia, both of them detected and identified in real time based on their individual signature, and they're highlighted with the different colors. So software can not only detect 1, 2, but up to 15 different compounds in real time. So quite a powerful software. So that's the first step, basically, detecting and identifying the compound. Next, we move on to the second step, which is from all the pixels that were tagged um, to a given compound, then we want to extract from that the concentration. And that's the way we do it. So it's to extract what we call a column path concentration map of the gas plume. So those, the answer will be in terms of concentration times the depth of the plume. And I'll have an image here to explain that in a few seconds. But basically what we build here is we make ourselves a little model of the scene, composed of the different layers that the camera measures. So basically every layer is responsible for producing infrared energy that ultimately reaches the camera. So the first layer is what we call the background. So the background is whatever lies behind, or solid objects, or whatever lies behind the gas plume that we're trying to measure. So this could be a building, trees, the blue sky. So this is what we call the background. Then after that, we add a layer of, well, the gas plume itself, which has a given depth, and a given concentration of gas. And then we have the atmosphere that is between the camera and the background, and the camera and the plume. So the atmosphere is composed of gases, water vapor, carbon dioxide. All of those compounds emit and absorb infrared energy. So we have to add that to the mix. And then we have this complicated or not so complicated equation that describes the scene. So basically, on the left-hand side, you have your radiance, total radiance that the camera will see. If you add the contributions of the different layers, do the math, you end up with an equation that looks like that, summing all different contributions. Now, in the different components of that equations are unknowns and known parts. So, but unfortunately for us, there are a lot of unknowns. So things that the camera cannot isolate. So for example, we have to know, in order to solve that equation and get the parameters of the plume, we need to know the temperature of the background. That's an unknown. We don't know that unless you go out and probe it. We don't know it. We need to know the gas plume signature, the concentration, and the depth of the plume that we're trying to measure. And we don't, these are all unknowns. The temperature of the plume itself, that is a factor in equations. We don't know that either. Again, the concentration, signature in the atmosphere, or we might know what the atmosphere is composed of which gas, but how much, how much water vapor do we need to put in to explain the measurement that we have? We don't know how much carbon dioxide, what temperature, what pressure. All these are unknown at this stage. So there's a lot of unknowns, unfortunately for us. But there are some knowns, and we can exploit the fact that we have a camera. So the camera sees different part of the image, and we can extract very valuable information from different portion of the image. For example, the background, we know there's just plume in here, so we can go to the side where there's no plume and extract the temperature of the background this way. And there's quite a number of ways, clever ways that we can use the data to extract or to constrain the equation a little bit more. But ultimately, we're able to do a mathematical model of the scene and really extract from the measurement and all our clever deduction. We can extract the properties of the gas plume itself. So we can extract the concentration and the temperature of the plume. The only thing that we cannot tell from this camera is how deep the plume and what's the depth of the gas plume. That's why we quote our results in terms of concentration times the depth of the plume. That's why I have here on my little chart the gas plume in gray. I know we will extract the concentration of that plume in terms of ppms times meters. If we knew the depth of the plume, we could divide that by the depth and get the concentration in terms of ppm. But we don't know that. There's no way the camera can tell how deep the plume is. But it's not a big problem because we know the field of view of the camera. We know what the pixels represent at a distance, and we can calculate from that the total mass of gas in the plume. So let's say the camera tells us that this is methane. We know the molecular weight of methane, so we can calculate for each pixel how much methane there is, even though we don't know the depth, but we know the surface. So we can say that this pixel contains this much grams, this much gram of methane, for example. So that's the ultimate answer from that second step. I know it's sometimes it isn't easy to understand, but I can always go back to it if need be. Oh, I made a little mistake here. This should read step 3. So step 3 is taking our measurement, our column path concentration that we've determined in step 2, and then factoring in the velocity of the gas to come up with a gas flux measurement. So for example, in this little image, you see we've got some kind of chimney that emits the gas. We draw like an imaginary rectangle, that's the yellow rectangle. And then we calculate in that rectangle how many grams of methane, let's say methane, how many grams of methane there is in that little rectangle. And by, again, exploiting the data that we get from the Hypercam, or knowing the gas displacement velocity, which in some cases we can take in as the simple wind velocity. So let's say for that day, the wind was 5 kilometers an hour. And then sometimes we approximate that gas displacement velocity by 5 kilometers an hour. Then we multiply the amount of gram in that rectangle by the wind, or by the gas displacement velocity. So that will give us how many grams per time crosses that, or enters and exit that imaginary yellow rectangle. So that's how we are able to produce grams per hour or kilograms per hour of gas. Well, I hope I didn't bore you too much with the details. Now, let me just present to you some experimental results that we managed to get over the years in different applications. All right. So I'll begin by first presenting to you some experimental results that we got from ground-based measurements. So one question you guys might have is, were this technology ever benchmarked against other technologies or against real results? Well, the answer is yes. Of course, throughout the years, we've participated in a number of campaigns to exactly measure how precise we were with, let's say, our gas flux measurements were against in situ measurements. One of them was Total, in which we've participated a number of times on their technology, or on their platform or test platform. And you can see here an example where methane was leaking, accidentally leaking this time, from the release apparatus, and we were able to tell them, "Hey guys, there's a leak going on," and they surely they came in right away and fixed it. And the second one is, or second example I'm showing here, is from the National Physics Lab, in which we perform various measurements at various flow rates, various backgrounds, stuff like that. So of course, results were very good. You can see here the releases in that, the kind of releases that were tested between 0.03 to 5 meter cube per hour from those experiments. So this kind of technology can be applied, and after testing it, of course, benchmarking it, we've applied it into in various applications. Showing you here just a few. Of course, oil and gas industry, detecting methane and other VOCs. You can see here an example of methane leaking from a distribution system, natural gas distribution system, side of a building on the right-hand side. Looking at flares also. So either just determining the amount of unburned methane, for example, coming out of a flare. We've also tested determining combustion efficiency from flares from this technology. So a very safe, non-invasive way of doing the measurement. Just we're in that case, I think we're located 300 meters away from the flares. Of course, landfill, the top example here is methane leaking from a collection pipe installed in a landfill here in the city near Quebec City. And the one on the right-hand side is a newer application in which we look at sulfur dioxide emissions from vessels, from ocean-going vessels. I'll present on that a little bit later. Yeah, I was talking about Total. Here's as an example. Yeah, you should be able to see the video playing. So as I said, we've participated a number of times with Total for their experiment. And you can see here, in this case, we brought in 3 different hypercams on site to measure methane releases. And by positioning them all over the site, we were able to produce a 3-dimensional, or the guys here that worked on that at Total, they were able to produce from the data gathered, collected in real time, to produce a 3-dimensional cloud of the gas that was released. Of course, the gas properties are always measured at the same time here, so we know the concentration, and you also know how the cloud moves as a function of time. So very neat application there. Just to show you how good also the measurements were in a context of looking at smokestacks. I've got here 2 examples. One of them is, you can see here, looking at stacks from a distance of, I think it was 500 meters away. So the Hypercam is there and installed on the tripod, looking at the exit portion of the stack. And what's nice here is we've got the spectral or the estimation from the camera, but also in situ measurement to compare against. And you can see here quite a good agreement between results obtained by the camera and the in situ measurement for sulfur dioxide, nitrous oxide, and carbon dioxide. Very good agreement. So not too bad from a camera working at 500 meters away. Second example that we've got here is some work that we've did a couple years ago here, looking at the incinerator here at Quebec, burning burning all kind of stuff. So it's the same concept. We deployed the Hypercam from just the roadside, looking at the 4 stacks there. At the time of recording, only 3 of them were measured. That's why you see the 4th one on the right-hand side. There's nothing coming out. That's normal. Again, you can see pretty good agreement between the measured parameters from the Hypercam for water vapor concentration and CO2 flow rate, carbon dioxide, between our measurement and typical data released by the organization running the incinerator. Next, I want to quickly show you the results we obtained on a series of measurements that we made in the port of Rotterdam a couple years ago. That experiment was to spend, I think, a week in the area, just driving to different locations, trying to find unknown VOC emissions, and surely enough, we found some interesting ones also. So as I said, this is deployed on the scene for a week, driving around. You can see the image here of a typical deployment. Hypercam on the tripod is powered from the vehicle. And we just basically, I was just panning the Hypercam at different locations and trying to isolate and find unknown emissions. And I'll show you a couple that we found. The first one is from an NTBE, or from a tank, a storage tank. It was filled. It was in the process of being filled with MTBE. And when looking at the top of that storage tank with the Hypercam, we found a leak. One of the components at the top was leaking methyl tert butyl ether, or MTBE. In that case, we were located 40 meters away, looking at the top of the tank. So we were able to, in real time, when I was there, we were able to find the leak, identify it as MTBE. And after that, we ran our quantification algorithm, and that's the image that you see here. So it's MTBE leaking at and the concentration from each image you can see there. And in the plot below, I've calculated the flow rate based on those measurements. And you can see here it varies as a function of time, just because the wind varies. And in this case, we've taken the gas velocity to be equal to the wind velocity. So that's why we were able to compute this. So the blue line is the calculation, and the bounding areas of the blue area is just kind of gives you an idea of how it's to represent the fact that the wind may vary. So it's kind of an error estimation here. But what's interesting here is that at this location, there are 3 MTBE tanks with a combined estimated annual emission of 9,900 kilograms per year. So that's, if you do the math, that translates to a flux approximately of 370 grams per hour per tank. And you can see here what we've measured agrees pretty much with that average emission rate from that tank. So although we didn't have in-situ measurements for this is an unknown leak, we're able to tie it back to what the company says the emissions from those tanks are. So good, again, a good validation. Another type of measurements that we've made here, same kind of idea here. We're located 350 meters away looking at chloro-difluoromethane, so F22 emissions. And you see here quite large emission of the gas. And you can see here it was pretty windy day, so it blows all over the place. And again, we were able to extract the flow rate from that from that emission. And unfortunately, here I don't have any in situ or measurements to compare against. And let me take you here on in a landfill. So those are measurements that we've made in a landfill here near Quebec City. This is a particular landfill in which a collection system was installed to collect the methane gas that is produced by city law. And they were required to do so. And we were brought in to measure if the system was performing well and if there was leak. So this is an image of a pipe that was leaking methane. You can see here the detection images in black and white and purple and kind of pink color, and the corresponding, again, corresponding concentration map. Red, of course, means high concentration. If you go towards the blue, it means lower concentration of gas. Again, same kind of algorithm or same kind of mechanism was employed here to determine the emission rate from this source. And so this is all great, but the examples I was presenting so far were all very not I'm sorry, I'm looking for the word, not diffuse, but very located releases. Here, an example, I just want to show you that to you. This is a diffuse emission. So methane here is not coming from a single point source, but it's coming from the lake. So it's decomposition of organic material in the lake that produces the methane, and it bubbles up from the lake and it mixes with the air afterwards. So this group here at Linköping University, they were able to quantify the emissions coming out from the lake, and you see here those are very small emissions. So even though the examples I showed you before were focused on very large emissions, the instrument is able to produce very precise results and for very small emissions. Here we're talking methane emissions here from the lake at the same level as the methane that's naturally present in the air. So it's very small um, increase in methane that was recorded here, and their results are published in Nature Climate Change a few years back. Let's switch gear here, and I'll show you one example of how this technology can be used to detect sulfur dioxide emissions from the maritime industry or from ocean-going vessels. So here in Quebec City, we're located near a very important seaway or a place where a lot of ocean-going vessels pass in front of the city. So this is where we were located for that kind of experiment. You can see our location here indicated by the yellow star. We're located in the port of Quebec City, and we were looking at ships as they went along, going back to the sea after delivering their goods. And the little video that I'll play here is you'll see the ship pass by, and you can clearly see sulfur dioxide being emitted from the chimney as it moves. Sorry, there it is. So that's the camera. Of course, because the ship is going by, we tracked it a little bit, but you can see the plume, the pink plume is SO2 being emitted in the air. And here the camera is located 200, I think, more than 200 meters away. So that's all good, but maritime industry has a very specific regulations for sulfur dioxide emissions, and it's not in terms of sulfur dioxide per se, but it's in terms of sulfur in the fuel, the regulation. So by doing clever estimates and clever math, we were able to detect, or to, based on our detection of SO2 in the plume, we're able to infer the sulfur concentration from the tank, from the fuel tank of the ship, and then tie it back with the regulation. And yeah, again, I won't bore you with the details, but here's the ship. Again, it's the same kind of basic principle. Here we take an infrared image of the ship as it goes by. We focus on the gas plume escaping from the chimney. We determine the concentration here, and I'll just show you graphs for those who like graphs. But we're able to fit the model, make a model just like I've described before, and then extract the properties of the gas plume, and then infer what is the sulfur content of the fuel, because in the fuel there are sulfur molecules, and these are not burned by the combustion processes inside of the engines, and the sulfur just makes its way back in the atmosphere. So if you calculate the sulfur dioxide in fuel in plume, you can determine how many sulfur molecules were in the fuel, and the ships have to declare that value. You see here the BDM, what we call BDMs. So bunker delivery notes, when they fuel up, the companies tell them what the sulfur percentage is, and in that case, it was 0.09% sulfur in fuel, and we can compare that with our measurement, and our measurement says it's very close to that. You can see here the dashed green line is the actual declared ratio, and you can see our measurement just hovering above and below that value. So very, very precise results. And we're still working on that to build up statistics and measure a lot more ships. So before concluding, let me show you just 3 examples here of using that technology, not from a ground perspective anymore, but working from the air. Of course, from the air, it gives you a total new perspective and really opens up the possibilities as more ground can be covered. You can find a whole completely different emissions. So for that, we're using the instrument that I've presented before, same kind of technology, but this time works from the air. And it's installed in fixed wing aircrafts, helicopters, or drones, very small package that we called the Hypercam Mini. And you can see here the kind of information that it can reveal. So on the right-hand side, you see this plume being detected from an oil and gas rig here on the right-hand side, and on the left-hand side, you can see each when we detect an emission or when we detect something, GPS coordinate, exact GPS coordinates of the gas plume itself are logged into our system, and we provide, of course, the imagery in high resolution visible imagery, but also high resolution infrared imagery, the gas plume indicated on it, precise GPS locations of all the detections that we made. So these detections would be here, all the little red dots on the Google Earth overlay. So this is the kind of information that a system can produce. Of course, from the air, multiple gases is still possible. You can see here an example. Well, I think there's 3 different compounds detected in from the air in real time. So acetone, ethylene, and methanol. Of course, each color coded with their own colors. Here. The airborne instrument works in 2 different ways. So I'm just giving you here a heads up. So one of the mode of operation is what we call mapping mode, and this is a mode where, as the aircraft flies along its path, the system will record individual images, and then we put all of those images together, stitch them up to create a large area mosaic. And this is kind of what you see here overlaid on top of the Google Earth imagery. So in that case, you see the infrared imagery composed of individual, here in this example, I think it's 10 individual measurements, and with the gas cloud indicated here. In this case, it's methane at 10 grams per second being released. And this was recorded 900 meters up as we flew above this site here. And this is a Total site in southern France. The other mode of operation is a mode in which the system can lock on a specific ground coordinate and then is able to produce more images as a function of time, more than one image of a single point on the Earth. And this allows you to get a better understanding of the dynamics of the plume or the dynamics of anything, basically. So here's an example. Here is a methane plume, methane emissions. And you can see it if I click. Yeah, you can see it change form as from cube to cube just because the wind was blowing quite hard. But you can see how this gives you, can allow you to get a sense of the dynamic of the thing as the aircraft flies. So very neat application here to have, or very neat, opens up the world of possibilities here. All right, so let me conclude here and maybe have a few minutes for questions, conclusions and key takeaways. Yeah, so as I presented at the beginning, so at Telops, we've established ourselves as a world leader in thermal infrared imaging solutions. So our Hypercam and Hypercam Airborne Mini are passive infrared sensors. So it allows you to reach hard to or to reach to get or to image hard to reach structures in a hazardous environment in a safe way. So now we're at a point where our detection and identification and quantification are solid solutions, proven effective in various applications in various environments, and provide precise values of gaseous emissions, either for all types of greenhouse gases, organic volatile compounds. So yeah, and the solutions now is built in real time for the gas detection and identification and quantification as well. So you see here various examples again of the images we've been collected over the years. So on that note, I'd like to thank you very much for your attention and presence here today. So questions are more than welcome. At this point, I'll take a sip of water while I try to access questions that might have come up during the webinar. Sorry. All right. Yeah. I'll take the few questions here. I'll read them out loud. One question here is, what is the spectral range covered by the Hypercam? Yeah, good question. Sorry, I didn't say it. So many things to say in less than an hour. But yeah, so the Hypercam we've been using here is our long wave Hypercam. So the spectral range is from 7.7 to almost 12 microns. So it's and we also have midwave, but there's only one question that only one slide I've presented with the midwave. So it's mostly long wave Hypercam, 7.7 to 12 microns. I'm just browsing today. Yeah. Are there any compounds of interest that infrared can't measure? Any elements of compounds that are problematic? Yeah, I did not spend a lot of time talking about that, but yes, of course. Well, as the name implies, greenhouse gases, it means they trap heat, and if they trap heat, they absorb or emit some level of infrared energy. So we're basically able to measure pretty much all greenhouse gases out there. But each of them, because they have their own signature, some of them are better than others at absorbing. If they're better, That means they absorb a whole lot, and we can detect them very easily. Some compounds out there, like H2S, is one of them that often comes to us, um, as it has a signature in the long wave, but a very faint signature, and so we can't really detect it. It's just we would need an instrument that would be 100 times more sensitive to detect that compound. So yes, there are some compounds out there that we can't detect, and some of them also that often are asked are diatomic molecules like N2. Then we can't detect those molecules. They don't have an infrared signature. Um, Yes, one question, can you calculate 3D gas volumes from 2D images accurately? Yes, good questions. I've showed you the example where we had 3 different cameras. That was from a first experiment that we did at Total. As I said, we came back several times with other experiments, and the first one we brought 3 hypercams. The second experiment we did is we brought 2 of them, and the idea here was to still get a 3D picture, but with 2. So the way we went about that is we had one fixed hypercam looking at the gas plume. The other one was to the side, maybe 90 degrees out to the side, and grabbing one image of the gas plume, static, storing that into memory, and then we would move that camera to another location. So that way we were able to assume, kind of have a ghostly image, if you want. Of course, that image wouldn't be updated as time went on, but at least it provided us an image with which to work to kind of estimate that 3D that 3D imagery. So that's how we went about doing it with only 2 cameras. But of course, it's not as precise as having 3, but it's a lot less expensive. How is the information sent from the detector to the computer, given that the temperature can be very high? What is the physical link between, sensor and computer? It's a standard a camera link, nothing fancy, standard equipment. So the camera transfers data on camera link, which is a very high throughput standard for transferring data. So we haven't seen any problems with temperatures. As I said, this instrument has been used in very cold and very hot environments. So on that front, it's we haven't seen any problems with temperature so far. In fact, the only problem we've seen is the operator operating in the desert environment. It's harsher for him than the equipment. Yes, question. Do you rent the system or is it subscription, a purchase? Yes, we have several offers. Of course, you can buy one if you have the budget. Yeah, we have a couple instruments here for rental. We have a part of the business is renting, and there's several options, of course, associated with them. So if you can rent the equipment alone, you can rent the equipment with an engineer that goes to your site and help you perform the measurements. And also, you can rent the system, the engineer, and the data analysis from that engineer. So it's quite the flexible package here. We're pretty open, so it can be subscription. If you need it several times throughout the years, we can work on with you to provide a kind of a subscription-based model. Yeah, how accurate are the identifications? Well, the identifications of the gases are pretty accurate because, as I said, the gas signature, every gas signature is as a individual signature. So the Hypercam is able to, as I said, split the light into different channels. So you obviously split the infrared radiation that comes in into thousands of individual spectral. You can fit that spectral. You can fit the measurement very nicely with the signature that we have in our library. So because every signature is individual, then you can really distinguish. You can resolve different signatures very easily. The only problem, say if you have 2 signatures that are very close, to each other, then that might confuse the software. But so far, we haven't seen any signatures that perform in that way. So not with typical hydrocarbons or VOCs. Pretty much all of them has at least one distinguishing features, and for which the algorithm can go to work on. Is there, if there are newer custom signatures we'd like to explore, is it possible to access raw data from this system? Yes, so as I said, the signature database that we're using is based on Hypercam. This is just the basic infrared signatures that we provide. But if you're interested in having a custom signature, if let's say if you have it, you can import that into the software. Or if you want to have a look at the signatures that we have, for sure, we can send you or contact me, and I can send you a sample data package for you to explore, play around with, and see what it can do for you, for sure. Does it have, yeah, a good question. Does it have the ability to quantify particulate matter from stack emissions? Yes, very good question indeed. So this, the ability to, because particulate matter, those are very small particulate, micron-sized particles. It doesn't behave like a gas, of course. It's not semi-transparent or anything. It's just a solid particle that you're trying to image. So it's the mathematics behind it is not the same as detecting gases. So we have to go down a different road, and that not many people have been on that road. So there's it's still not sure on that. So some research is going on right now, and I know there's a group at Waterloo University that is working on that very subject. And indeed, we have an upcoming webinar with them. So yeah, I'll if you're interested in that, reach out to me, and I'll be able to provide you with the information. But yeah, so this group will talk about their recent discoveries. But at this point, I still haven't seen very good results on particulate matter quantification from hyperspectral imagery. But yeah, research is ongoing. So. Yeah, are there? I don't know how much time we have for this. I think we wanted to keep it under an hour. Just let me know, but I can do a few more. So are any regulatory entities using your technology for emissions enforcement? I'd say not so much right now. From the oil and gas industry, the technology is still being reviewed, I think. We're still, I think we're getting there. It's especially those aerial surveys are getting more interest these days. But I think it's still not used as a hard enforcement. But it's getting there. Technology, more and more people use it and verify it against in situ measurements. So it will get there eventually, just like OGIs now are around. I think this kind of technology will be there in a few years maybe. And in the maritime environment, we're still working on that. It's very new to them, so having this kind of equipment, just from the maritime application, the old way, or the way to do it, is still to go aboard the ship and take a sample of the gas and bring it to a lab and have the answer sent back to you a few days after. So that's the regulatory way to check fuel compliance. Now, doing the same thing from 500 meters away with the camera is a different beast. So we still have to work with the authorities and get the word out there and prove ourselves. But I think, yeah, same as the oil and gas, I think it's an interesting new way, and yeah, people have to get to know it and test it out and make sure it works for them. So I see there's more questions. Maybe I won't have the chance to go through all of them. Sorry.
Well, what we can do is, well, for those that are still in the call, the information, phone number, and email is on the screen.
Yeah.
And then we can also provide you with the questions you didn't get to answer, Jean-Philippe. And if you want to reach out and answer separately, you can do that. And also just keep in mind, as mentioned, this is the first in a series of 3 webinars. So stay tuned for announcements on the other 2 webinars. But thank you, Jean-Philippe, for this presentation. And thank you, everybody who joined us today. As a reminder, we'll send out the PDF version of the slides as well as the recording of the presentation later this afternoon. Again, if you have any questions, the information is right there. Feel free to reach out to Jean-Philippe after this webinar. Thank you and have a great day.
Perfect. Thank you very much. Bye.
Bye.